So once again, welcome to this month's the Cloud Security Webinars technical track meeting. Our topic this week is Secure Enclaves. I'm Dale McCarty. I'm the Membership Director for the Cloud Security Alliance, and we've got some other directors on with us, but feel free to throw any questions out you might have for the CSA chapter as we go through this. Secure Enclaves, I know it's a topic that I am not well versed in, so I'm looking forward to today's presentations. And we have three speakers today. Terence Spies and Richard Minner will kick us off this morning, kind of overviewing what Secure Enclaves mean and are. And then Steve Van Lare is going to be taking us through how people are actually implementing them. So looks to be a great overview. I will tell you up front that these presentations are available online, already there on the CSA website, and we will be adding the videos from these presentations later in the week. So now we'll move on to our presentations for today. I'm going to stop sharing, so Terence, you can share. And our first presentation is by Terence Spies and Richard Minner. Terence is a technical strategist for csa-orv and was previously the CTO for Voltage Security. He's been implementing cryptographic security systems for 25 years and was the original architect for Microsoft Crypto API, the Microsoft Certificate Server, and the secure channel systems for Windows. He is co-creator of format preserving encryption and has built systems that protect sensitive data in payment, banking, insurance, telecom, and healthcare systems. Joining him is Richard Minner. Sorry about that. Richard is a software architect with csa-orv Voltage Security, bringing 40 years of software development experience to building enterprise data security solutions. His roles have ranged from engineering director at some smaller firms to senior software engineer at Google. Richard holds several software patents, including co-inventor of Voltage Secure Stateless Tokenization, which protects PCI data across the payments industry. Gentlemen, the floor is yours.
You're on mute, Terence.
Terence?
He's muted. Give him a second here. Hope you can hear me.
We can.
Yep, I hit the magic unmute button.
There it is.
Actually, I was doing a presentation a couple of weeks ago with a company, and they actually had a company policy where they find you $1 every time that you have a mute button on. So, but if I did that, I think I would be broke. So,
One more try.
Okay, can you guys see the slide?
Yep.
Okay.
Yes.
All right, so let's try that again. So welcome and good morning, everyone. So we're going to divide the presentation today into two parts. The first thing that I want to talk about is something more broadly called confidential computing. And one of the things that I have to apologize for here a little bit is that this is a relatively new concept. And one of the things that you'll find is that there are lots of people that have ideas about what things should be called in this. So I may interchangeably use the terms trusted execution environment, confidential computing, and enclave, although most of the times I will just say enclave. That may mean different things in different contexts, but hopefully that's clear by the end of this presentation. But let's talk about what the issue is here. And it really is a fundamental one. So when we talk about confidential computing, we're not talking about one particular small application or one aspect of security. We're really talking about thinking about security in a fundamentally new and different way that has been enabled by new hardware modes that are actually accessible now, that if they're utilized can actually change security from the ground up and enable us to design systems in quite a different way that will not have some of the fundamental security problems that we have right now. So I've talked to a number of people about enclaves and confidential computing, and I think the best place to start is what the actual problem is. And I know that many security presentations start this way, but part of the issue is it's sometimes not evident to people sort of how in the clear everything that we do is. And one of the reasons that might not be clear is that we're taught to design systems in this sort of way, where we think of an application and some data, and that application can be any number of things. But the application and data interacting with each other within a security boundary, and we typically think of that as a particular server or machine, and that the application is relatively sewn up and safe, and that the data and the application have this sort of private interface, and the user interacts with that through some hole in the security boundary, and we call that the attack surface. And this is a sort of a convenient way to design things, but it really fundamentally doesn't reflect reality, and we'll talk more about what that means. But the basic problem is that the attackers don't have to honor our abstractions. So we can design systems in these kinds of ways, but the attackers are not bound by the boxes that we have drawn around things and the way that we think about things. So in particular, I'm sure everyone here has experience with the fact that privileged users can log onto a machine, and once the privileged user is on there, they typically have access to essentially everything on the machine, the application and the data, which creates another attack surface. If you're in the cloud, or even if you're in an internal data center, someone with physical access to the machine can use any number of set of tools to directly read memory, directly read disks, intercept network access, things like that. And other attackers can use things like side channel, and there are routine operational things that we do with data in terms of backing that data up, moving it, replicating it, that move the data off of the machine. So our box diagram really doesn't reflect the real world, in that the application and the data are actually shared and visible in a lot of different ways, and we've created these abstractions that try and hide this or make it easier to think about application security. But what we found in the past is that this continues to not work because people find their ways through and around this. Well, confidential computing is an attempt to solve this problem, I don't want to say once and for all, but solve it in a fundamental kind of way that really goes back to actually creating a wall around the application and creating a wall around the data that is enforced cryptographically rather than being enforced by the security boundary of the machine. So how we currently solve this abstraction problem is, unfortunately, in some cases, we create more abstractions. And what I mean by that is we're going to add things like anti-malware, antivirus, user behavior monitoring, any number of these tools to the machine in an attempt to track what the machine is doing, track what the user is doing, and in some sort of probabilistic way, get to try to detect anomalies in terms of, hey, something is going wrong here, my abstractions are failing, or some user is violating what I think of as the security boundaries of this particular application. One of the other things we can do is we can try and encrypt data, and there are certainly any number of tools that will encrypt network connections, encrypt disk volumes, or data items like tokenization. And we can even go so far as to use something called the hardware security module. And the hardware security module essentially goes and says, I'm going to enforce this abstraction by creating another computer with a very limited amount of functionality and a very strictly enforced hardware boundary around it, in terms of we'll take a computer, we'll wrap it inside of a tamper-proof module, and we'll actually do physical things in order to prevent access to the memory and the internal working state of that computer. And that will work, but hardware security modules necessarily become slower, and they're not really places that you run applications. They're places you run very small key management modules, typically, that are then going to feed keys into these things. And then you're back into the same problem in terms of how does my application keep a secret? How do I maintain this if it's not running inside of the HSM? And then there are any number of security monitoring tools that will work outside of the PC or the server. And another thing that people try and do is this idea of boot security and trusted platform modules, where we're going to say we're going to try to enforce the integrity of that security boundary by booting the system cryptographically, having the CPU check the BIOS before the BIOS comes up, and basically building this wall. And that can be useful, but you also run into a bunch of complexity problems. And these boot security modules also don't do anything about physical access to the box in terms of somebody being able to basically directly read your data out of memory. So current security architectures attempt to what I would call simulate private computation. They attempt to build an application and data boundary and then sort of try and stick things on the outside of the boundary in order to make that work. Because what we really want is we would like trusted atomic programs. And what I mean by atomic is you can ask a program to do something, but only a defined set of things, as opposed to jumping into the program randomly or changing the program. That we understand what program that we're using, and that program operates on what I call opaque data. I can only access the data that program is accessing through the program as opposed to through secondary side channels. And maybe the cleanest way to think about this is a database, right? We would like to think of a database as something that has a query interface. We can send it queries, get back results. We can set access control lists around those queries, what users have access to what pieces of data. And that is honored, as opposed to, in reality, what can happen. You have administrative users, or you have side channels that enable you to directly read the database backing store, or read replicas or shards of that, where it's not atomic. But what we want to use some of your time this morning is to explain two important technologies that are being deployed now. That enable us to move from simulating this idea of private computation into something that's actually real and cryptographically enforced. And actually having these technologies, I think, really, it's not, I don't think it's overstating the case to say, could potentially really revolutionize how we think about security in terms of building systems where this idea of atomicity of programs and privacy is enforced cryptographically through something that we can actually prove, as opposed to through software mechanisms that we continually kind of layer on top of this. So the goal of this talk is to communicate why it's important and how it's going to affect how you build systems. In our first part, we'll talk about the problem that we just described in a little more detail. We'll talk about, take a little sidetrack to talk about something called homomorphic encryption that people have probably heard about, that attempts to solve somewhat of the same problem. And then we'll talk about what's an enclave and how these things are implemented now. And then Steve is going to get a little more practical in terms of, with these technologies, how do you build systems within this new architecture. So to explain why this is important, we actually have to rewind a little bit and talk about computer architecture 101. And I'm going to grossly oversimplify things here in the interest of time and complexity. But what we want to get to is what the sort of root of this problem is. So we can model a computer in, again, a grossly oversimplified way as a central processing unit that actually does a computation, a memory management unit that does some important things we'll talk about later, and a memory, which RAM or other kinds of storage, but RAM is the important one to the central processing unit. And what happens here is that your CPU basically has a job, which is to fetch instructions out of memory and use those instructions to alter the CPU state and other parts of memory. And memory is just a list of bytes or other pieces of information indexed by an address. It's literally just a list of these things. And these bytes contain basically everything the computer can operate on, which is a mix of instructions that tell the CPU what to do and data that is going to be operated on by those instructions. And that data can, of course, contain interesting things, like in this example, we've got a password, the world's most popular password, stored in this memory. So available to the CPU to do computations on, but also available to anyone else that can actually read that memory. So in a modern computer, we want to run more than one process and have the idea of more than one user, which I've put under the larger category of multi-processing. And we'd like each of those processes to appear independent. So in the modern age, you can think of this as either processes in terms of processes within an operating system like Windows, or in a more modern sense, sort of this idea of a hypervisor is basically working in the same kind of way. And to isolate those processes, we have to create essentially unique views onto memory for them. So processes can't read each other's memory. They can't overwrite programs in other processes, things like that. And we want to be able to make that happen. And that's where the memory management unit comes in. And the memory management unit is going to create tables within hardware that's going to separate memory so that each process is going to see a different set of instructions and data, even though they're all in the same actual physical memory. And so the way that we'll arrange this is the CPU is going to boot up and is going to load some sort of supervisor, which has some set of instructions and data for how it's going to create other processes or other virtual machines within this central processing unit. And the memory management unit is going to map things around so that each process has its own view onto memory and can't interfere with each other. But the important thing to realize is that this is all sort of fictional in a certain sense, in that the memory management unit and the supervisor can really still see all of this memory. And certainly anyone with physical access to the box and the right kind of software is going to be able to basically pull all this out. And one good example is if the box faults or a CPU faults and you dump core, there's a core dump file which is not going to contain just one piece of memory. It's basically going to contain every page that the CPU and the memory management unit knows about. So if you had secrets inside of there, it's going to appear inside the core file, or it's going to be available to other tools that are able to look at actual physical memory itself. So I guess I covered this a little bit. So we have this need for a process to create this process memory map and the rest. So now we have sort of a basic kind of computer and operating system going. But it creates a sort of dangerous idea that things are actually separated and that there is a capability to actually create secrets. But it's not, because anyone that is a supervisor, and if you're an admin on a machine or you on the hypervisor, or if you are a cloud administrator, you're going to have access to all of that physical memory. So there really is no secret that can be kept there. And so why is this a problem? One is that there are inevitably issues with the operating system that are going to lead to unconstrained access, because you're simply going around these page tables that create this view into memory. Admins have too much power. And an operating system level admin can basically read all of the memory on the box. And then you have to start constraining those administrators, worrying about credentials for those administrators because they have the capability to steal data. And of course, the big one is that everybody wants to start moving things to the cloud if they're not there already. And cloud admins have physical access to the box and hypervisor level access to basically every single byte of data in memory. And as we start moving things to serverless and the rest, this gets even worse in terms of data is getting copied around everywhere and is not really private. And then there's 1,000 different reasons that you might want private data, privacy regulations, and the rest of it. And I'm not going to go over why you might want to do things in a private notion, but simply the fact that privacy is going to be a fundamental underpinning of anything you're actually going to do with data that actually matters. So one of the solutions to this problem, and I'm not going to cover this in a huge amount of detail, is that there are a set of encryption algorithms that allow you to actually do computation on data without decrypting. And this gets around this problem because we can take this kind of model where we're going to operate on encrypted data directly, where now if we can take encrypted data, move it to a machine, perform computations on it, and failure of the operating system or failure of admins or the rest of it is no longer relevant because all they can pull out of this is encrypted data. These algorithms are complex and they have important limitations both in terms of performance of the algorithms that can be run on top of them. But the basic model is this. So imagine that you have a fraud model that you want to run, and that fraud model powered by transaction data. And let's say that you have two banks that have transaction data that want to create sort of fraud scores or try to detect fraud inside of their transaction base. And they want to basically both use their transactions in order to get better fraud reporting. In a homomorphic model, what they could do is basically they both encrypt their transaction data into some private form. That gets moved onto a machine that you don't particularly trust, can be moved onto a cloud machine. And both of those transactions go into this homomorphic circuit that performs computations that actually create this fraud score data and output the fraud score data, but in an entirely encrypted domain. So if somebody breaks into that machine, they could disrupt the actual computation, but they can't get any of the inputs, the outputs, or the intermediate values of that computation, even if they have complete control over the machine. This is obviously super powerful, so they could do that computation and then basically return these fraud scores back to the bank saying, here is the result of basically combining both of your pieces of data in a private way. And the only thing they get out is a fraud score. So bank A can't see bank B's transactions and vice versa. But they get back the result of the computation. So this is in some sense the ideal world. If we could do this efficiently, this would be an incredibly powerful model of computation. But what we found is that these technologies, while having this power, are quite slow in terms of people talk about 10,000 or 1,000 times slowdown to the actual underlying thing, and work much better for particular types of applications. So for some kinds of AI modeling, it's actually reasonably efficient at doing generalized computation in terms of running, for example, a database that you're going to do a search on in this homomorphic way turns out to be quite difficult. So this may be something that emerges at some point in the future in a generalized kind of way, but I think is going to, for the foreseeable future, be limited to relatively, let's say, niche kinds of applications. But it is a solution to the problem in a quite.
I would just add that there is significant data expansion there as well, right?
Yeah, exactly. So you basically work in this encrypted universe where everything goes slower and is much bigger. Is there another way to do this? And the answer is yes. And this is what an enclave is. An enclave is an attempt or a technology that enables you to work within an encrypted data space without the slowdown or complexity of homomorphic encryption. So what we're going to do is we're actually going to add additional hardware to the CPU with something that I'll call an enclave engine. That enclave engine contains a set of keys and an encryption engine that can actually work at full bus speed to and from memory. So now we can, with these keys, create data repositories within memory that are encrypted, and that's what I've shown in orange here, is the CPU can move things in and out of memory encrypted in such a way that the only place it's decrypted is actually inside of the CPU die itself. So if I can read memory, I still don't get anything because basically all of that data is encrypted. And we're going to add two keys. One is a sealing key and what we'll call a signing key. So the sealing key basically encrypts transactions to and from memory. And we're going to create a special kind of execution mode that will execute something called, what I'll call enclave instructions after something called a signature has been verified. So what that means is that I can download these instructions or this program or this VM, whatever it is, to my CPU. And if I enter that enclave, that is, I call the program within the enclave, the CPU is going to swap itself into enclave mode. All of its transactions to memory are going to become encrypted. And I can only enter that in such a way that if the enclave has not been changed. So there's basically an integrity check that's done over that enclave, and that enclave is actually kept protected itself. So what does this mean? So one is that we have encrypted memory access, so someone can't actually read the memory. And there's a second, slightly more complex, but also important feature called attestation, which means an enclave can request that the CPU generates an attestation, or sometimes called a quote, which basically takes the state of the enclave instructions and digitally signs them with a key that is only resident within the CPU and will only sign enclaves. So This is going to allow us to create a cryptographic attestation that can be verified by somebody off machine that the program that they're interacting with is actually within an enclave, and that all memory that this enclave is interacting with is encrypted. And this is actually going to enable us to create secure systems where the supervisor or someone with physical access to memory can't actually read things. So if we want to create distributed secrets, we might have a key management server that has some key for some piece of data that we want the computer to interact with. We're going to load an enclave process onto our server. That enclave process will be cryptographically verified by the CPU itself. And all of its interactions will be with memory will be encrypted with an enclave key that will encrypt that. And we can create a TLS session, and that TLS session key is now going to be kept encrypted within that, so not readable by other processes on the machine. And over that TLS session, it can basically send a signature of what it's running, a signature of its actual instructions, and bind that to the TLS data, and then basically send something that's signed by the CPU, this attestation that says this is the exact binary that is running on this CPU, signed by the CPU itself, over a channel that is protected by the actual CPU's sealing key. So it's going to send that over, and the server at that point can then ask itself, is this a binary that I trust? Is this running within an enclave at the security level that I trust? And if it is, it can at that point ship the data key back over to the enclave. And now it has the ability to use that data key to decrypt access to data that you want to keep private. And some normal process that's not running in the enclave can then make a call into the enclave to say encrypt or decrypt this particular piece of data, or perform some interaction with this piece of data. The enclave will perform that operation, but all of its information is private because it's encrypted by a key on the CPU, and there is no way to change the enclave process because it's protected by the CPU. And the server that contains the data key and that wants to protect the privacy of that data knows that it only gave it to a process that's in this specialized state. So again, this is a little complex, but this has created something we couldn't do before, because now if I'm in this state and I am an admin with complete rights to the box, or if I core dump the machine, or if I zero-day the operating system or the hypervisor, it's irrelevant, because all I can do is ask the enclave process to do the polite things that it wants to do. I can't jump into other parts of the process, and even if I dump all of the memory, the keys and the data are not available to me because they are all encrypted with a key that's locked inside of the CPU that will only do encrypt and decrypt operations for the enclave itself. So my data is now private in a way that it was not private before. And I have a way of proving that I'm in this privacy state to a key server that's going to give me access to data, which allows me to build distributed systems that might operate over databases and things like that. So this is a huge step, and allows us to do any number of other applications where we want to keep data private, which range from database and privacy kinds of applications to one of the original applications for this enclave was to actually protect, for example, data on 4K DVDs. So in that case, a 4K DVD, the actual drive itself is going to confirm that it's talking to an enclave before it gives up any of the data on the disk. The data on the disk goes into an enclave, is decrypted there, and then basically pushed out, in some cases, encrypted to another enclave on a GPU that actually then pushes it encrypted to the monitor. But that gives us a way to protect that data where no other process can read the data that's coming off of the disk for the movie. It can be played, but nothing else can happen to it. And that's in contrast to, for example, the way that older DVDs were protected with this CSS process that most famously failed because the keys that were being shared were just basically encoded on the disk itself in a way that they were trying to sort of hide it or make it obscure. That ultimately didn't work because people simply copied that path. And those kinds of attacks are not available here. So you can think of that same model for doing rights management over a DVD could apply to an enterprise database or other kinds of data that you want to keep private. You simply say the only access to this is through an enclave, and it has to go through these authorized channels, and all of the interactions with memory are going to be private. So how do we implement these? And Steve will talk about some of this in some more depth. But we would like to basically have an enclave process not have to be built from scratch. So there are these things called library OSs. And a library OS basically gives you the ability to create RPC channels, to read and write unencrypted chunks of memory, to talk to a network interface, to access other servers and talk to a file system, which gives you the ability to actually read and write encrypted and unencrypted data. And so this allows us to actually take a process that we care about, move it into an enclave, and then have it protected in this way by the CPU itself. So now that we understand sort of what this thing is, the art then becomes what moves into the enclave itself. Because what you would like to do is move things into the enclave, have it give it access to this kind of private data. But then the question becomes, am I going to just move other bugs into the enclave? So the question then for system architects becomes, what part of my application moves into the enclave? How do I assure that what's in the enclave is not going to give access to data that it shouldn't give access to? So you may end up coming up with these sort of cores or security kernels for your application that are going to enable you to do this stuff, as opposed to move everything over, or the other opportunities to move everything over and attempt to lock things down into lower access or lower functionality kinds of levels. But the basic technology net is here, but it can end up creating some important questions in terms of what moves into the enclave and how does that work. So I might want to pause here for any questions in terms of things that weren't clear, because we kind of went a little bit into hyperspace here in terms of going from one model of computation to another model of computation. But I think it's important to understand these basics before we go any further. Is this reasonably clear to people, or are there questions that I can answer right now while this is fresh?
Well, one question for you, and obviously this is a computing environment, assuming this can be done in the public cloud, and if
Yes.
so, is it all the public clouds who can provide a secure enclave, or is there only one or two of them currently doing it?
So I would say, and Steve can fill this in more detail, essentially every public cloud has some ability to run enclaves. Unfortunately, there's not just one enclave model, and this is going to play exactly into Steve's presentation with respect to how do you actually implement these things. One of the challenges is that Intel and AMD both have enclaving built into their CPUs. Apple has enclaving built into their CPUs, but they have different models for how these enclaves are built, how they live within the process and the rest of it. But if within Azure and within Amazon, they both have public enclave strategies. Google is actually using enclave technology and is increasingly exposing that. But they are, let me say this, not incredibly easy to use right now, because you end up having to do some things that you could previously gloss over in terms of what goes into the enclave, how to architect my application to do this. And also, when we go back, one of the things that the server had to do was have a policy with respect to what binaries do I actually trust. And this is not something that we really had to ask before, because we really didn't have the capability. You just said, basically, I'm going to take a machine. Typically, if I wanted to share keys, I would take a machine, I would give some credentials to some of those machines, and they would simply use the credential, and the server would cough up secrets to whoever had a credential. In this case, we're going to get delivered back very specific information in terms of you are talking to this exact binary. So now you're going to need essentially a catalog of these binaries, which ones you trust, which ones you don't trust, what keys you're going to give to them, and that is going to end up becoming sort of the management challenge for this in terms of what specific binaries and programs should have access to which pieces of data in my system. And from a security point of view, that's sort of paradise in terms of you can lock things down to say only this version of this piece of software can perform these actions against, let's say, my HR database. But at the same time, you're now going to have a lot more information you need to manage in terms of if you change that binary in any sort of way, you're going to have to register the binary to say, this is v1.0 and v1.1 of my HR application. These are the hashes of the binaries that compose that, and you're going to have to manage that data. And there are a number of tools that will end up doing that, but that's going to be one of the challenges involved in using this in a secure way. But good question. So just to summarize part one, and went a little faster than I thought I was going to go, but that's good because it will hopefully give us some time for questions at the end. So the ability to keep data secret is fundamental to secure computing, and we have the problem right now that computers that we have right now basically don't do it. We sort of simulate it by saying that we have a security boundary around the actual machine itself. And we know that we can't really solve this problem with conventional processors. So, these two pieces of technology, homomorphic encryption for a relatively narrow set of problems, and confidential computing as a new CPU architecture for a very wide range of applications that are emerging. And as I just said, basically are to the point that you can now use these things within the cloud if you understand how to make your application enclave aware. So it can solve these, requires some deep thought about how systems and applications are structured. And that's going to lead us to part two, actually. So Stephen, I think we're on time. And I can transition things back to you. So I'm happy to take questions from you right now, or we can save them to the end until after Steve has talked and sort of do them at one time.
So if there are any other questions, please put them out in chat. Or feel free to come off mute and ask them at this point. And welcome back. So thank you, Terence and Richard, for giving us the overview. We're now going to move into the how you actually implement some of that cool stuff. So Steve, I'm going to stop sharing and allow you to share your slides. And while you do so, let me tell you a little bit about Steve. Stevens is the Vice President of Engineering for Anjuna Security. Stephen, did I pronounce Anjuna right?
Correct.
Okay, great. He brings 30+ years of unique experiences in creating products for enterprise software solutions and a deep knowledge of driving products through all stages of the life cycle, from concept and launch through multiple releases to next generation architecture. He served in both large and small companies, from security products like running global fraud and ID products for Experian to launching AI products at startups like Automation Anywhere. Steve, take us home, man.
Thank you much. Thank you for the intro, and really liked Terence and Richard's presentation, and we're going to try to build off of that and talk about what does this mean to you? What do you have to do to kind of embrace this technology? Just to recap into Terence's presentation a bit, the way we traditionally think about security is we think about perimeters. We think about the boundary that goes around our code. And for a very long time, that boundary has been associated with a device. So we protect the, who has access to the device. We put devices in cages. We put cages in secure buildings. When I was at Experian, we literally put moats around the buildings to protect the devices. And we've used the physical security of the device as a proxy for security, because we've known for a long time that once you have access to the machine, pretty much everything on the machine is fair game. Well, as we move to the cloud, that model is fundamentally broken. I don't know what cage my CPU is sitting in. I don't know what machine my code is running on. I don't know what admins have access to that machine. We don't think about it often, but somebody at Amazon clicked buy, a machine showed up, they logged into the machine, they configured it, they stuck it in a rack and made it available for you and I to use. And so when we think about things like what's my firewall, what is the concept of a firewall in the cloud when your data is commingled with everybody else's network traffic and admins? And there's a very unfortunate hack that happened a couple of years ago where somebody bribed an Amazon admin and they did some core dumps, exfiltrated some data, which happened to have a lot of credit card information and PII, and there it went. And all it really took to get access to it was bribing somebody that was in the circle of trust. So um, governments and militaries have recognized that this is a problem. They tend to build hardened hardware. HSMs is an example of that in the commercial space. In the commercial space, things are beginning to change. This notion of being able to protect memory while you use it is coming to the fore. So like Terence, I'm gonna try to standardize on the vocabulary today, but know that the vocabulary may be wrong 6 months from now. But when I talk about what's happening in the clouds, we're going to talk about confidential computing. Most of my presentation, however, is going to be about the enabling technology, the enclaves themselves, because it's the enclaves and the ability to protect and isolate memory that ultimately gives us a way to think about our security perimeters logically that go with the code and the applications as opposed to physically and going with the actual devices themselves. And this is a massive change of thought in terms of how we secure our systems, but it's one that I think is really important and one that I think is ultimately preventing some of the final largest compute workloads to move to the cloud, whether it be banking applications, whether it be governmental applications, because including the cloud in your circle of trust means thinking slightly differently. We at Anjuna are not the only ones to be thinking this way. One of the questions that came up in chat was, what cloud vendors have something here? And in 2019, all of the cloud vendors under NDA would talk about the fact that they've seen these chip changes coming along and they might do something about it. In 2020, all of them made announcements about what they're doing in the confidential compute space. Amazon announced in November, Azure announced in May, Google announced in June, Alibaba, IBM, Oracle, they've all made their announcements in terms of A, this is important, and B, they're going to be supporting it and they're investing large in making the capabilities available to all of us to take advantage of. The hypervisor vendors have all been adding support for this capability to the hypervisors. And the CPU vendors, they've been the ones that have been enabling this by creating the encryption subsystems and creating the isolation subsystems that we can take advantage of. So an awful lot is going on in this space, and it can be a little confusing. And so what I'm going to try to do is break this down into a couple of steps and really kind of define, what does this mean to us, the developer? What do we need to think about? What do we need to worry about? What are the different models that are in place? When I get to the end of the presentation, I'll show you how you might use a product like ours to cheat and ignore some of this and just kind of lift and shift applications into these environments. But even when you do that, you need to have some understanding about what an enclave is and what does it mean to the architecture. Terence did a great job of describing how to think about these changes and how to think about them architecturally. And I would encourage you, as you start embracing this, go back and look at his presentation, and then look through my presentation again, because it will give you a great starting point to contemplate how to approach this. So first thing I want to do is give you a model for thinking about what some of the capabilities are that are being added with Enclaves. And TCB, sorry, stands for Trusted Code Base. The Trusted Code Base is, if you think about your code, every line of code is a potential bug. It's a potential security bug. It's a potential functional bug. The larger that code base, the more you have to worry about. So the first thing you want to worry about is, what is the security perimeter that you have? If you don't have enclaves, your security perimeter is essentially the entire device. It is all of the operating system. It's all of the other programs that are on that machine. It's everything associated with that individual device. So without enclaves, your trusted code base is everything that you've installed. It's the entire code base of Windows or Linux or whatever operating system you choose to run, plus everything that is there, Kubernetes, etc. You can draw your enclave boundary at a couple of different sizes. You can draw your enclave boundary at a virtual machine. And so the enclave is managed by the hypervisor, and what's inside that virtual machine is what's your trusted code base. You can draw that boundary at a container and say, I've got multiple pieces of code that are running on this machine. I've packaged the trusted pieces of code up as containers, and I'm going to run them in their own and unique way. The final level you can be thinking about your enclaves is wrapping around an individual thread or an individual process of your application. And in those cases, you can get pretty narrow in terms of what you want to protect. Now, obviously, the smaller you go down that triangle, the more you have to think about your application's architecture, the more you have to think about what the components are that you're working with and how you want to tease them apart. The higher up you go on that, you're working with more macro level concepts. If you're working at the VM, you're really thinking about the hypervisor. If you're working at the machine, of course, this is the security that we know today and we use today. The other thing that you should consider is there's a couple of attributes about enclaves that are interesting. The first is isolated access. So how does the technology you're using actually provide this access? How isolated is it? And some enclaves are more porous than others. And what I mean by that is, in a very restrictive sense, some enclaves, if another process attempts to access your memory, they're going to get a segment fault. They're going to get a page error, and their program is going to stop at that point in time, and they won't be able to access the memory. Other enclave technology, when you go to access another process's memory, you're going to get access to encrypted memory, but you won't be stopped from accessing that physical memory. So what is the isolation model is different with the different technologies, and it's worth thinking about because it does have some implications. One of the questions that came up in chat was, what are the CPUs that support this? The one that most of us are going to run across are Intel's SGX editions and AMD's SEV editions. And both of those add some capabilities that protect you from the system admin. So your process can be running, and the system admin, even with root access, can't get to what you're doing. Some of the chips provide a hardware root of trust, and we'll talk about this when we talk about keys and why this is important. Terence talked about this a bit, but having a private key embedded in the CPU enables us to think about how we bootstrap our security models a very different way and in a very useful way. Both of those technologies also add memory encryption, and it's important to note that not all enclaves provide memory encryption. There's different ways to go about isolation, and memory encryption is one of those ways. SGX from the start has offered memory integrity, whereas AMD, that came later in the S&P release of SEV. And memory integrity, really, there's two things associated with this. One is, do I have any guarantees that nobody else can tamper with the memory? So when I want to measure the code I'm looking at, how much of a guarantee do I have there that there's not another process that, even if there's encrypted memory, if a process can swap out data, it can try to manipulate your application in adverse ways. And so the memory integrity is part of what you want to think of. So these are attributes that I'm going to talk about in the next couple of slides as I talk about what is an enclave at the bit level. And once we dive down into the bits, I'm going to step back up and talk about how do we think about the systems that these enable for us. I won't go through the slide. I won't do that to you, but it's worth looking at later. But the important thing here is when we think about security, we've all been trained to do the same thing. We've all been trained to follow the data. Wherever the data goes, how have I protected that data? Unfortunately, most of those protections end at step 2. If step 1 is I encrypt my data, so my data is encrypted at rest. Step 2 is I pull that data into memory, but then to process it, I have to decrypt it. And at that point in time, my data is available for other processes to snoop on. That is, in fact, how the SolarWinds hack worked at its core. The hackers created a process that could watch the compiler's memory. And when it saw the compiler was compiling a particular set of files, it would swap them out for a different set of files, let the compile finish, and then it would put the original files back. So if anybody ever looked at the logs, if anybody ever looked at the files on the machine, the files that came out of the source control were the same files sitting on the disk that the compiler worked with. And the fact that there was another process watching memory to swap out the files on the fly was how they got away with what they did in terms of putting the back door in place. So protecting memory is really important. Protecting against the admin is very important, but you should also be thinking about what happens with your files, what happens with your network traffic, so you can build a complete solution. Okay. So let me talk about what hardware enables enclaves. This is ultimately the enabling technology that all of us are likely to engage with. The one that's probably the most well-known is Intel. Intel has created SGX. They launched it in 2015. It's been through about 3 iterations since then, starting out initially on desktop machines and then later moving to server class machines. The most recent release is Ice Lake, was announced in April here of this month. Last month. AMD has their competing technology called SEV. It's a different structure. It came out a little bit after SGX. AMD tends to get their chips out on an annual basis. So there's been an annual update of SEV every year, adding new capabilities and adding new things inside the chips. ARM, I'm going to talk about this in a minute. It's a little bit different, but ARM has a capability called Trust Zone. That is its enclave capability. And then Amazon created a capability called Nitro Enclaves. So this is not actually the CPU, but if you know the Amazon hypervisors, they've offloaded some of the work of the hypervisor onto a set of hardware called Nitro. And they've then introduced a set of capabilities called Nitro Enclaves that's built into that hardware and built into their hypervisors. So it's a hardware solution that absolutely most of us are going to touch at some point or time in terms of what they're doing. So that's the hardware that we're likely to get engaged with. And while I'm talking, feel free to interrupt me at any point in time. I don't have the chat going, so if somebody wants to bug me if there's chat messages that come up, I'm happy to address them now or at the end.
Why don't you keep going? We're kind of assembling some questions, but I think you're answering some of them as you go here, Andy, or Steve. So
Super. Okay. So let me talk about Trust Zone. Trust Zone was the first consumer use of Enclave. So it is most likely the first Enclave that any of us experienced on the iPhones. When they started putting the biometrics, they took advantage of Trust Zone as part of the ARM chips and embedded into the CPUs or embedded into the iPhones the ability to store all the biometrics secure and do the actual biometric validation inside an enclave. So very much a great use for enclaves, because literally if you take the phone apart and you get a bus analyzer out and you try to watch the bits going back and forth and extract the biometrics, all you're going to get is encrypted data. The challenge with ARM, and the reason I put it up here first, and we're going to kind of blow through it and then kind of forget about it for a bit in this conversation, is ARM doesn't actually design chips. ARM produces specifications, and then different manufacturers create different chips based on those specifications. And so to think about what is an enclave and how do you take advantage of it in a trust zone situation, really you're going to need to be thinking about the specific chip and the specific implementation of Trust Zone that chip provides, and then how you take advantage of it. So if you're going to be going down this path, you're likely going to be looking at some assembly code. You're likely going to be looking at some low-level code to enable the capabilities that you're after with the chip. So this is mostly going to be in the IoT world. We'll see what Apple does now that they've rolled ARM out into the Macs. So they're likely to introduce a commercial use of enclaves there. We're likely to see something out of Amazon as they continue to push ARM use inside their products. But when we talk about Nitro enclaves, you'll see why they're not likely to do it at the ARM level. They're likely to more take advantage of it at the Nitro level. But that's Trust Zone, and let me move on to the next one, SGX. So SGX is Intel's answer to how do opcode or how do enclaves work. What you do, the model that Intel first assumed that we were all going to adopt is we were going to take our applications and we were going to split them into two parts. We were going to split them into the trusted part, and we were going to split them into the untrusted part. And we were going to take the secret bits of our applications, the things that we really cared about, the keys, the biometrics, the whatever, and we were going to put those inside the trusted part of the application and leave the rest of the application unmodified. And so the assumption, the model that they built was an assumption that we would be rewriting our applications to take advantage of SGX. And so with that, they made a number of assumptions about what kind of things would be okay and how do you provide the trust. So what they've done at a physical level is they actually take a block of physical memory and you say, here's the starting address, here's the ending address, and that block of physical memory will be encrypted. And any other process through the memory management units, whether they try to sneak through it through a virtual access or otherwise, if it actually accesses that physical memory, they'll get a page fault. They will not be allowed to access that trusted environment. Only the processes that created the trusted environment is going to be able to execute there. So it's a pretty robust amount of isolation that they put in place. They went to the level of saying, if the operating system is not part of the circle of trust, and the things that are green on this chart are the things that are encrypted, if the operating system is not part of your circle of trust, your trusted code base, then you don't want unlimited access from the trusted environment to the operating system. So a bunch of opcodes, there's roughly about 20 opcodes that are prohibited inside of the enclave. And then there's a bunch of new opcodes that have been created that enable you to get inside and outside of an enclave and deal with registers and deal with cleaning data so that it's not exposed accidentally when you work on that boundary. So your untrusted part of your application is basically going to be the piece of code that needs to create the trusted enclave. And then inside the trusted enclave, you've got to do some low-level assembly work to swap out the opcodes and help the application do what it needs to do. Intel has an SDK to make this easier to do, but it's still a lot of work. And you're going to need some low-level kernel hacker type folks to kind of build what you want to build. But very robust model in terms of the isolation, very robust model in terms of the encryption and the protection. I mentioned here the hardware attestation of the application. There is an opcode that does the attestation, and attestation gets used a lot, but it's really a very simple concept. What you're going to do is when I ask the CPU to do an attestation, it's going to go through and it's going to generate a hash of the trusted memory, basically. And it will take that hash and it will sign it with the private key that's embedded in the chip, the root of trust. And that signature can then be verified through an independent channel back to Intel to verify that, yea, verily, this was a Intel CPU that generated this measurement. And so when you get the measurement, you can cryptographically prove the chain of trust back to Intel that this was a trusted piece of hardware running in a trusted way. And you have a known set of code that has landed inside the trusted environment. So very powerful capability. It's lovely to have it supported, and it's critical to how we think about the security model down the way. So this is SGX. I'll take a quick breath here, and then we're going to switch into SEV. And AMD took a different approach to how to secure and create enclaves. The Intel approach is sub-process. So if you remember back to the chart where I had the size of the TCB, the model that Intel assumed we were going to all work with would be we were protecting an individual process or an individual part of our application, the smallest possible TCB that you could entertain. SEV took a different approach. SEV took the approach that the boundary that's interesting is the virtual machine. And when you turn on your virtual machines at the hypervisor level, there is a different key for each VM, and the memory for each VM is protected through that encryption. Now, that makes for a very straightforward compute model. You don't have the enclave entry and exit. You don't need the assembly language programmer to get involved in porting your application to take advantage of these capabilities. But you do need to bring more to the table cryptographically. You need to do a bit more work when it comes to the attestation process to make sure you get what you need. You need to do a bit more work on the isolation. The virtual machine, the hypervisor can get access to the contents. Other processes can get access to the contents. They only see encrypted data, but they can tamper with it until you get to SMP. When you get to SMP, there's a guarantee against tampering. And that makes SEV significantly more robust and something that is a big advantage. So the key takeaways here for SEV is you're thinking about a virtual machine, and the virtual machine is the logical entity that you have to work with. The downside to that from a cloud computing point of view is your cloud vendor is going to own the virtual machine. The cloud vendor is going to own the hypervisor. Very rarely do you buy bare metal when you rent instances in the cloud. You usually get a encrypted, or you typically buy a VM because when you get resources from the cloud, they're going to give you a virtual machine and say, here you go, here's your virtual machine. And you can turn on the encryption and you can bring your own key to that encryption, but it behaves like a virtual machine. So the real guarantee you have at that point is if somebody gets access to the machine, they can't do a lot, but people can still get access to the encrypted bits and they can still pull those out and start working on those. So there's things to think about there, but it's a really compelling model from a simplicity point of view in how to move forward with this. The last one I want to talk about is Nitro. There's no green on the chart because there's nothing encrypted, but there is a very strong isolation model that Nitro provides. So the hardware is supporting the hypervisor, which makes the hypervisor a good bit leaner and meaner. But what happens in Nitro, what happens in Amazon is you create an EC2 instance. And then from the EC2 instance, you create an enclave. And the process that creates the enclave says how much of the resources of that EC2 machine are you going to put into the enclave. And then that separate VM is not accessible to anybody. It's not accessible. You can't get to the operating system. The hypervisor can't get to it. The only communication you have to that enclave is the local channel. So it looks very similar in that regard to what SGX did. There's a trusted and an untrusted portion of your application. Inside that virtual machine, it's mostly a full version of the Linux kernel. The things that have been removed are the file system and the network system. And that's so that there aren't any inadvertent holes that somebody can drill through to get to the operating system. So you can think of your kernel as a functional environment from a functional coding perspective. It goes in there, there's no access to it. You can't configure it. Nobody else can configure it. You know, you've set it all up in your build environment and then you just let it run and your application runs on top of that. But the challenge here, of course, is breaking your application into two pieces. Since there's no network subsystem and there's no file subsystem, the programming model is essentially you need to create a private API that's working over the local channel, which is a socket interface. And you need to create APIs for everything your application wants to do, and then put a handler for that out in the host VM that has access to that local channel. And you get to work at that level. When you go to package it up, everything is packaged up with containers. So from a cloud perspective, it's a very simple model to think about. You can build containers. Containers go into enclaves, and that works pretty simply. Attestation is supported by the hardware, and it's integrated into KMS. So there's a really simple model for bootstrapping the applications and getting started with what you need to put together. So that's the last of the hardware components that we need to talk about. Like I said, each one is a different model. Each one implies a different thing that you need to do to your applications to get it into an enclave and then go and secure it. As Paul Harvey would say, and then now for the rest of the story. There is some fine print in all of this, and I'm going to talk through some of those details. I'm going to then do a quick demo, and that's probably a great point to pause for a whole bunch of questions. But a couple of things to think about. The first thing is enclaves are just a box. They will run whatever you put inside of the enclave. The enclave itself is not a panacea. It's not going to solve all of our security problems. It redefines the perimeter of how we think about security. But if you have an application and the application takes the credit card information that happens to be sitting around that it's processing and spits it out to the log files, enclaves aren't going to solve that problem. If you've got cross-site scripting problems, if you've got other leakage problems, Those are all things that the enclave isn't going to help you with. The enclave is helping you isolate things that you don't want in the trusted code base into what you're doing. But the box itself, you can put anything that you want inside that box. Since we're going to work with a locked box, the next thing you need to think about is your build environment. Your build environment, it needs to be a trusted environment. And you want to think about it as two different pieces, because attestation is going to tell you that you're running a trusted piece of code. What you put into that box to go run, you want to then be a trusted piece of code, which means you need to create a trusted piece of code, and you need to know what code you created and have a way to measure it and deal with it all the way back at the build environment in terms of what you're putting together. I'll talk about this a little bit more in a moment, but your build system definitely needs to factor into what is your security and how do you take advantage of enclaves. Containers, just containers are your friends. One of the lovely things about containers is it's the easiest way for you to know that you actually know what your trusted code base is. When you go through the process of creating a container, you need to understand, what am I basing my container off of? So which operating system, which kernel? You need to know what libraries you're going to be adding and what components you're going to be adding for your application to take advantage of. So it is the easiest way for you to get your arms around what is your code and what is the code that you are dependent on, and how is that separate from the things that you want to put outside that trusted code base. So even if you don't run your application from a container, if you're just going to install code on a machine and run that code in an enclave, the container is still the easiest way to know that you've actually captured everything that you need to trust. Containers can run whatever you put inside of them. The code that you put inside the container, or the code that you put inside an enclave, if you use a mechanism for lift and shifting applications inside the enclave, you can run that code outside the enclave too. And so you want to be careful to make sure that that application, if somebody takes it outside the enclave and tries to run it, it's not able to do the secret things that you want it to be able to do. And so Terence talked about the attestation process, releasing a key. I'm going to talk about that again here in a minute. But you want two things. You want to know that you've got trusted code, and you want to know that you enable that code to do its job only after it proves its identity. Once it proves its identity, you give it a secret, and that secret allows it to access the things that you want it to access. And that enables you to protect against somebody trying to take the code out of an enclave if they manage to get a hold of the code and run it somewhere else and get it to do something and believe that it's secure and operate. But you need to be able to protect for that, and that's the way to do that. The CPUs have embedded keys in them, and this is really, really cool. The fact that all of us have the same problem today without keys embedded in the CPUs, that you need a secret to bootstrap any security system. And so what do? We take the secrets and we put them in a secure vault somewhere. We stick them in an HSM, we lock them up, we put them in a nice secure place. We use a nice secure protocol to get the keys out. But what is that protocol? Ultimately, that protocol is sharing a secret with the key vault so you can get the secret that you want to bootstrap your application. Well, where do you store that secret? Well, that secret, you can't store it in the vault, because then you've got the same problem again. Do you store it on the disk? If you store it on the disk, maybe you should encrypt it. What do you encrypt it with? You encrypt it with a key. What key is that secret? Where does that one get stored? Well, can't store that one on disk next to the first one. So we all build this chain of obfuscation for all of our security systems today. You know, do I have multiple people type in a secret at different terminals before we enable something? Having a private key embedded in the CPU, the CPU architects were thinking about programs that would run on a single CPU and taking advantage of that key to do your encryption and do things. But if you're running in the cloud, you're running distributed applications. You're running applications across multiple CPUs. If you shut the application down, bring it back up, you're not guaranteed to get the same CPU, so you're not guaranteed to get the same private key. So you don't want to encrypt your data with that private key. But having that private key and having a method through attestation to prove back through Intel, through AMD, through Amazon that you are running where you think you're running, you can use that to bootstrap your secret process and use the identity of your enclave, the identity of your code to get your initial secret. Very cool way to get started. And then finally, just a reminder that memory protection, that's the new shiny object that everybody's excited about. But the real goal is not protecting memory. The real goal is protecting applications, protecting the data that the applications are processing. So when we think about the perimeter, we should be thinking about the entire perimeter. We should be thinking about the perimeter of what's the process in memory, what's the data it accesses, what's the network connections that it makes. All right. So let me jump into the next slide here. The importance of key management. I talked about this a little bit. Terence talked about it a lot. The keys that are bootstrapped in the CPU, they're the ones that we want to use to get us started. Really simple problem that all of us are going to face. If I have a distributed application, I am likely to have either multiple components that are accessing the same data, or I'm likely to have multiple web services that I've scaled up my load that are talking to a common database. They're talking to common data files across my application. Obviously, we're going to encrypt the data with some sort of key, and using the attestation process, we can get the keys bootstrapped to each of the enclaves. And the process of having the applications prove their identity. I am the piece of code you think I am, so I'd like access to my key, and then it gets access to the data, does a couple of things for us. It allows us to decouple the code from the data. It allows us to scale horizontally, and it allows us to not have these user applications access the data if they're not in an enclave in terms of what they're doing. So very important aspect to how we think about this. And when we draw your architectural pictures and you think about your scale, definitely think about the code independent of the data and what keys do you need for which keys do you need to get the applications started, which keys do you need to access data. I mentioned way back at the top of this that we were going to separate the notion of confidential computing and enclaves. Enclave is the enabler. Confidential computing is what all the cloud vendors are essentially offering to give you the ability to take advantage of enclaves. Of course, in the context of the cloud, we're thinking large applications. My last fraud application was 20 servers for a minimum configuration for searching for fraud in online transactions. So it was a very distributed system, and we all operate that way. Enclaves work really well in this environment. So what you need to do is you need to package up the code that you wish to run, including the code that's going to launch the enclave, into your containers. Stick them in your pods for Kubernetes and deploy them that way. And then the real thing that you need to worry about is making sure that the host systems have the CPUs that you need to run the cloud's hardware that you want to run. So Google, Microsoft, Amazon, they all make this really easy. They specify a particular machine type that has access to enclaves. They enable through their various versions of Kubernetes a certain amount of awareness so that you can target your pods towards enclave-enabled hosts and spin them up in a relatively simple way. And so for us, the developers, what we need to worry about is getting our code into the container, packaging it up as a pod, and then measuring everything that's in that container as what is our trusted code, and then using that measurement ultimately as the tool to release keys and get things started when we move things forward. CI/CD, I mentioned this was one final step. We all go through very similar steps. We take our source code, we compile it, we deploy it, we run it. The things that we add when we add enclaves, and the green ones are the encrypted steps, is we need to add a measurement step before we distribute our code. So when we compile our code and we package our code up, we need to measure it. And that's going to produce a hash that we're going to say, this is my trusted code. And so obviously, as part of our encryption subsystem, as part of our security worldview, that measurement has to be inside your circle of trust, whatever that circle of trust is. The admins that have access to it, the locations that you run it. If you run that measurement on the same server that you're going to run on, and then you push the key up to KMS, and then you later pull that same key down from KMS, you haven't necessarily created the separation that you want to create. So if you think about decoupling those two steps, I compile, I measure, I deploy my code. If my code's been tampered with at that process after that measurement, my enclave isn't going to run. And so we can trust that everything in between from that measurement to that attestation really can't affect us. But once we attest it and we get to the other side of it, we know that we've got the code we wanted to have in the place we wanted to have it, and then we can run it, do what we need to do. So let me do a quick demo at this point, and I'm going to show how to put some code in an enclave, how easy it might be. And I think we can stop and take some questions at that point, or maybe I'll do a quick commercial on what Anjuna does, and then we'll go from there. But let me start here. So what I'm looking at is I have a terminal window. And in this terminal window, I'm going to run Redis. Very straightforward database application. Redis itself does not have the ability to encrypt your data. And Redis is renowned for being super fast. And it does that by storing everything in memory. So in the original model of security where you trusted the machine, that's completely sufficient. If you don't trust the admins on the machine, I'm going to show you what you can do with that. So I'm going to launch Redis, and I'm going to put some data in it. So we're going to take Musk's social security number, phone number. So if anybody wants to get a hold of his content, feel free. Then we're going to dump the memory. And as an admin, I'm just going to do a core dump. And this is, in fact, the hack that happened up at Amazon a while ago. And I'm just going to grep in that core dump. I'm going to look for the keys that I put in place, full name, Musk name, social security number. And sure enough, I can find Musk's name. I can find his social security number. I can find his address in there somewhere, at least part of it anyways. And pull that out and look at what we're doing. Obviously, that's not the security we want in terms of what we're doing. And this is what the premise of enclaves are going to be. So last thing is I can look at the disk and everything's there. But let me look at the memory now. I'm going to launch Redis. I'm going to configure Redis to encrypt the database files. Speed this up a little bit. Great. our software has a configuration file. So I'm just going to load the configuration file. Boom. Skip over this. And then I'm going to launch Redis into an enclave. So what's happening here is my software is going to create the enclave. And then we're going to bring just enough OS in with us. This was the library OS that Terence talked about, that we can make it look to Redis as if it's working with a full operating system. And then we're just going to run the Redis command line inside that environment, bring Redis in, and launch it. So we create an enclave, we bring Redis in. I can see the enclave is running now. I can get information like how much memory do I have, trusted files that we brought with it. I'm now going to do the core dump. I'll put some data in there. Then I'm going to do a core dump. And I'm going to look for name. I'm going to look for social security number. I'm going to look for address and not find it there. And I'm going to look on the disk, and the disk is going to be encrypted. And so what we did there was essentially create a simple enclave, put some code in that enclave, allowed that code to operate like it's operated before without modification, and then modified its behavior. We modified its behavior, so we encrypted the files on the fly for it, and we encrypted the memory, taking advantage of SGX encryption, and put that in place. So the short answer, there is a lot of fiddly bits in working with enclaves. There's a lot of great material. One of the challenges, though, people are facing at the moment is the market is moving very fast. AMD is shipping a new chip every year. Intel is on their schedule for getting out major updates in this space. As I mentioned, all of the cloud vendors rolled out their initial capabilities in 2020. They're all updating those capabilities here in 2021. What Anjuna does is Anjuna will create the enclave.
Hey, Steve, let me
Yep.
interrupt you just a second, because I want you to get your commercial in. Very important. We all know that. But there are a number of questions, and I think we were kind of waiting till after your demo.
Yep. Let's do the questions.
And then we'll absolutely give you some time here at the end. So actually, and a couple of our guys have a number of questions, and I know you and Terence were answering some of them as we went through the different presentations. But let me start with Andy Gill. Andy's asked several questions, and Andy, will come back to your earlier ones in a minute. But one of his latter ones, and I quote, "Maybe I missed this or it was implied in your mention of APIs and sockets. I'm not a programmer. But how do you get stuff in and out of your locked box?"
So getting stuff in and out of your lockbox is the trick, because every lockbox is different. SGX's is different than Nitro's, is different than Trust Zone, is different than what you're doing with Nitro. So forgetting about the details for each one of them, that was the commercial part I was getting to, was ultimately you need to have code both inside the box and outside of the box that knows what the hole is and how to get data through that hole. So if I use a simple example, in the case of Nitro, the hole through the isolation is a socket interface. And so you need a piece of code on one side of the socket and a piece of code on the other side of the socket that your application will talk to. So one of the things that Anjuna provides is we provide a network piece of code. So you could put an application inside of Nitro. It will talk to what looks like a standard network interface, and we will proxy that to the outside untrusted part of the world, and then allow the network traffic to go on as if the application was living in the outside world as opposed to living inside the lockbox. But that ultimately is the trick you need to think about, and what the developers need to worry about is what modifications are required to the application, or what open source or other libraries can I use to make that job simpler.
Yeah, it's in some sense a fundamental security policy question, because if you're going to say, I'm going to put this in the enclave, it's critical to define what are my interfaces and what can I get into and out of this thing. So the edge of the lockbox is actually an engineering question, but also a security one that has to really be thought through.
And I think Terence's picture way back at the start of his presentation was probably the best one to think of. When we think of our applications and our APIs today, we don't think of the fact that there's lots of other ways people can get to our applications, whether they watch our memory, whether they watch our files, etc. When you put something in the lockbox, the only way to get things in and out of your program is through the APIs. So the APIs the application provides need to get ported through whatever the hole is in the enclave, so people can get access to it.
And Steve, I would add that in the TLS case, because we talked about this, that the TLS is terminated inside the enclave, such that you're basically that key, for the TLS connection itself is not, is not exposed. It's actually part of the communication.
Correct. So one of the things you definitely want to do is so if you have a network connection to the outside world, and you have an application, and your application calls the operating system to set up a TLS connection. Well, if you don't trust the operating system, making a clear text connection to the operating system to have the operating system make an encrypted connection off the machine, you've missed the perimeter. So when you put the application, so when you put the application inside the locked box, you want to bring your certificate for your TLS inside that locked box with you, so that the connection for the network in and out of that box is encrypted from the get-go.
Okay, so Andy, did that answer your question? Feel free to come off mute if we're lacking anything on that. You had also asked about specific CPUs, and I think Steve did touch on that. Your third question out there was having to do with memory. I believe it was, excuse me, there are a number of questions here. Having to do with
Client-side memory?
Yes, client-side memory.
So the enclave exists on whichever box you put the box, has the enclave capability. So enclaves aren't so much about client and server. Enclaves are a fundamental capability of the CPU. So if you wish to build a system that takes advantage of enclaves on the client and takes advantage of enclaves on the server, you can certainly do that with the technology that's available today. Most of what we see in terms of businesses that want to work with us is they're securing applications in the cloud, and the client connection into the cloud is going to be via TLS, because you're going to make an HTTPS connection to the service that's running in the cloud. And so decoupling the client side and server side there at that point.
I would add also that the trust does run both ways. I mean, it depends on your architecture, but the idea that a server can actually attest its identity as well. Like a client can know what server it's talking to in terms of the actual binary and so forth. So it just gives that capability generically, sort of like what you're saying, Steve.
Yep.
So Steve Lodine had several questions. One was about low-level data inside of the cloud providers, and I think Steve, you actually started answering that one during the first presentation. Anything you need to expand on?
I know there was a question about encryption of data by the cloud providers. Is that the one you were talking about?
Yes.
Yeah, because so we're in the encryption business, and we answer this question a lot. In encryption, the value of encryption fundamentally comes down to where the key lives. And so if your cloud provider is encrypting memory, that can be fine in terms of physical access to the box. But it's still the case that if you have a hypervisor or trusted admin, you're essentially inside that encrypted world, so it can still get access to the memory. These enclave things are complex, but you really have to have encryption and attestation. And this separation that we're talking about in order to get those benefits. You can't just straight encrypt memory. Actually, the newer set of Intel CPUs, Ice Lake, has an ability to encrypt all transactions to and from memory, to a program on the inside, to a trusted privileged user. You can still see all of that memory because you're essentially inside that encrypted bubble.
Okay, and then Terence, you were on chat talking to Chris Kiley about how do you assign or provision identity in an enclave?
Yeah, this is. I started answering the question, and then he asked again, and this is, I think, a fundamental and fantastic kind of question.
Yep.
Because, and I'll go a little bit. I'm sure that Steve has things that he can add here also. So I think from a practical point of view, the thing that Enclave solve is this idea of attempting to embed credentials inside of applications. So almost every security thing, if you dig inside, there's something hidden in the corner somewhere this is how I authenticate this particular program. Enclaves get rid of that identity, that idea of identity enforced through a credential, and replace it with, I know that I'm talking to this binary and it's in an enclave and it's private, so I can send secret things to it. So the identity is fundamentally the actual specific binary itself, or the hash of the binary, to be a little more complex. And then you start thinking about, okay, if I know I'm talking to this binary, I know its memory is private, are there additional things I need to know in terms of, is it on a specific machine and the rest? You might be able to do that. But I would say that you aggregate identity up from the fact that you know that you're talking to a specific binary that's operating in private mode.
And when we have really touched on is that the trust anchor here really ends up being the hardware vendor, because it's like a cert chain that's rooted at some known, signing the chip, signing the thing all the way up the chain.
And so one of the advantages you get is you've always got to trust somebody in a cert train. But if your hardware is coming from a different person than your cloud, you have two different paths, and it's kind of a second factor identity at that point.
Yeah, and if you don't trust your CPU vendor, you have other problems.
You have other problems. Yeah, you're kind of done. I don't know if there's another question. One that I did want to underscore that we sort of touched on is part of this identity management. We move the problem, the focus of the whole thing then becomes this catalog of which binaries do I trust. So that system ends up being kind of critical, because we already have to do this in terms of, somewhere you have to store shared secrets or passwords or whatever, and that system is critical. But this catalog, or I'm not sure what the right term is right now, of known trusted binary, measured binary pieces, that ends up being the real root of your system in terms of, these are the binaries I trust. So you have to manage that very, very closely.
Yeah, there's a lot to manage, and there's a lot of pieces, and I just to maybe underscore the value of what Steve and Anjuna are doing, is I really think in terms of enclaves, we're kind of back in the era of PCs when people were messing with, does anybody here remember config.sys? And loading.
Only the old guys.
Exactly. Loading device drivers and memory managers and the rest back in the sort of DOS extender days. So I was at Microsoft in the Windows group for 9 years, messing with all of that stuff. And using enclaves now reminds me a lot of those days a little bit, in terms of there are a lot of pieces that have to be set just right. Now, enclaves are powerful enough that it's worth doing it, but I think what you're going to end up seeing is that a lot more things are going to start living inside of enclaves, and there's going to be a lot more tool chain built up in terms of you're not going to have to deal with these details because the abstractions will get built up in terms of
Right.
I'm just going to run this thing and I'm going to say, please run this in a secure and private mode, and things will get configured underneath. And it's going to take a little while to get there. But I think from a security practitioner's point of view, it's quite important to understand some of these details, because this is how you're going to assure somebody that, okay, this data can't be decrypted. Why can't it be decrypted? Because it's running in an enclave which does the following sorts of things. This is sort of the fun of being a security guy, is that you have to understand those details. But I think over time, things like Anjuna and the rest of it are going to build this ecosystem where you'll be able to run things without particularly having to think about it, except from a security point of view.
And with that, Steve, we promised you a couple minutes. Why don't you tell us a little bit more about Anjuna, and we'll wrap up.
Yeah, so one of the things I want to say is this is a nascent space, and there's a lot of people doing some amazing things, but they're running in slightly different directions. And the risk there is people wait for everything to settle out. I am, I've spent an awful lot of time in my career helping secure systems. It's one of the things that attracted me to this business. As Terence pointed out, the tool chain is being built up to help make this easier. And so if you look at my career, I haven't spent much time in tool businesses, so this is a new one for me. But honestly, I joined it in part because I felt it was really important to get more tools in this space out there. And whether it's one of the open source tools or one of its our tools that you use, I absolutely think everybody should be looking at enclaves and working on ways to make them easier to use. I'll continue to focus on that, but if people take advantage of it. So I think that if you really want to boil down what Anjuna's doing is our CTO got a PhD in trying to take enclaves out of the world of let's deal with opcodes and let's deal with the cryptography, but how do you run a complete application in an enclave? And so we use different techniques for SGX versus SEV versus Nitro to make it simple. But the goal is to be able to take your application intact and run your application without modifications inside the enclave that you choose to run it in. And that then places the burden on you to think about, now that I've changed my security perimeter, how do I think about the architecture of my applications to take advantage of this new capability, as opposed to how do I take advantage of this new capability? And the distinction there is, if I can make it simple for you to get into an enclave, you can worry about the keys. You can worry about the overall ecosystem. Do I need the client and the server to know who each other are for my application? But really begin to think about what is your security perimeter and how to take advantage of that security perimeter, and what the implications are to cutting out your admins and cutting out the cloud vendor from your circle of trust.
Well, great. And well, first of all, thank you, Steve, Terence, Richard. You guys did a great job on teaching us today about a topic, quite honestly, I think we were woeful in. So appreciate you guys doing that. I will mention that out in chat, we do have some links that, here we go. We do have some links to a number of things, including, once again, if you want to win a $100 Amazon gift card, please go out to that link. The URL is actually in chat, as are the links for our website and the PowerPoint presentations you saw Terence, Richard, and Steve give today are already out there if there's something there that you need. Once again, guys, thank you very much. That was a tremendous 2 hours of overview. and love it that you guys work together. That first we got the overview of the technology, then we got how it's actually implemented. And I think that's really useful in our technical track pieces. So thank you again for that. Last thing for the group is our next event will be at the end of July. Once again, a little bit of a departure from our normal webinar approach. We are going to be doing the ComSpark Cybersecurity Summit in conjunction with ComSpark CDO Magazine and Detroit CSA. If there's anybody who would be interested on sitting on an executive level panel for some of that, please reach out to us. We're still looking to fill the last couple slots of that, but we've got about 65 presenters signed up for that. So that's going to be a really, really good and robust event. With that, I thank everybody for attending and hope everybody has a great day. See you next month.
Thank you.
Okay.